Using this storyboard strategy, this complicated looking mechanism is really only 2 steps long. Hey there, OChemNinjas. The Fischer Esterification is probably the most prototypical nucleophilic acyl substitution reaction you're going to see in the entire course. Unless you're one of my students, I probably don't know your instructor, but I can almost guarantee the Fischer Esterification will be on your exam. In terms of the net reaction, this is a reaction of carboxylic acids, and it is a preparation of esters. In terms of the setup of this reaction, it's important to note that this alcohol is a weak neutral nucleophile. That will be very important when we draw the mechanism later. This mechanism looks fairly long when we draw it out, and sometimes that intimidates students. But let's look at the net reaction and see if we can come up with a storyboard that will help us organize our thoughts. What I see when I look at this reaction is, in terms of a net reaction, one of the things that we need to do is to get this alcohol in. And the other thing that we need to do is to get water out of this reaction. These are the 2 key steps. Bring this alcohol into the carbonyl, kick that water out of the carbonyl. The rest of the steps are simply proton transfer steps that move us through this storyboard. I call them paperwork. If you're not familiar with the concept of proton transfers as paperwork, that's something I made up, and I have a link in the description down below to that video. Let's go through a sample mechanism for this reaction. From a mnemonic sense, we can predict the product of this reaction based on the storyboard we just talked about. This reaction is going to take this carboxylic acid, and it's going to add the alcohol to the carboxylic acid and kick out water as the leaving group. To get there, we'll follow our storyboard. The first part of this storyboard is getting the alcohol into the molecule. The Fischer esterification perfectly follows the story of the carbonyls. If you're not familiar with the story of the carbonyls, I have a video that I'll link to down below that uses the story of the carbonyls to organize all of your carbonyl-containing reactions in this unit. But in brief, we know things about carbonyls. Carbonyls are electrophiles. They're electrophilic at carbon towards good, strong anionic nucleophiles. Ethanol, though, is not a good, strong anionic nucleophile. It is not strong enough to directly attack that carbonyl. So what do we do about it? We add the acid catalyst. The first step in this mechanism is to protonate the ethanol with the sulfuric acid. This actually doesn't progress us in our storyboard at all, but we have to do it because ethanol is the most abundant molecule in the entire system. So statistically, when we add the sulfuric acid, the ethanol will get protonated before anything else. Our second step is to transfer that proton to the carbonyl oxygen. That forms our protonated oxygen intermediate. These first 2 steps were just proton transfers. They were just paperwork to set us up for our first key mechanistic step. The weak neutral nucleophile is not strong enough to directly attack the carbonyl on its own. But by doing these proton transfer steps, by filing this paperwork, we form an activated carbonyl that's more electrophilic so that even a weak neutral nucleophile can attack. That takes our resonance stabilized intermediate and turns it into the tetrahedral intermediate by adding in the ethanol. This nucleophilic addition completes step 1 of our storyboard. Step 2 of our storyboard asks us to kick out water as a leaving group. As I look at this intermediate, though, the best leaving group is this ethanol that I just added. I don't want this to be the best leaving group. I want it to stay. That's why I added it in the first place. But right now it's the best leaving group. So I need to make this not the best leaving group and make something else the best leaving group so that something else can leave. I call that the proton shuffle. To do the proton shuffle, we'll use the second equivalent of alcohol to take the proton off of the group that we want to stay in the molecule and put that proton on the group that we want to leave the molecule. The proton shuffle is 2 proton transfer steps, 2 paperwork steps to set us up for our second key step in the mechanism. Now that we have protonated this oxygen as a leaving group, we can drop a pair of electrons down from oxygen to kick out water as a leaving group as our second key step of this mechanism. This leaving group expulsion step kicks out the water and forms a protonated carbonyl intermediate. And this protonated carbonyl is also resonance stabilized. After doing the leaving group expulsion, we're almost at our final product, except this intermediate is positively charged. What are we going to do about that? We need to neutralize this charge by doing more paperwork. We'll take an equivalent of ethanol, use that to take the proton off of the protonated oxygen, file some paperwork, do a proton transfer step, and that forms our final ester product. Using this storyboard strategy, this complicated looking mechanism is really only 2 steps long. Bring the ethanol in, kick the water out. In order to do that, we had to file some paperwork, set ourselves up for each step along the way. But this story of the carbonyls and this storyboard strategy really helps simplify and organize our thoughts for this mechanism. The last thing I want to point out about this mechanism is to ask you how many of the steps in this mechanism are reversible. That's right, every single step in this mechanism is reversible. This is an equilibrium reaction. That means I can run this reaction in both directions. Starting with the carboxylic acid, I can add an alcohol and acid to form the ester. But because this mechanism is in equilibrium, I can start with an ester, add water and acid to convert it back to a carboxylic acid. That's called hydrolysis, a very powerful tool in organic chemistry. I have an entire playlist down below on hydrolysis that I'll link to. I'm not going to go through the entire hydrolysis mechanism here, but you can imagine it might go something like this. To turn the ester back into the carboxylic acid, I need to get water in and the alcohol out. Water is a weak neutral nucleophile, so it can't directly attack. But by adding sulfuric acid, I can protonate the carbonyl to make it an activated carbonyl so that water can attack. The water would form an intermediate where water is the best leaving group, but I don't want water to be the best leaving group. So I can do a proton shuffle to take the proton off of the thing I want to stay and put it onto the thing I want to leave, the ethanol. Then I can kick out the ethanol to form a protonated carbonyl, and a proton transfer to the end gets me back to the carboxylic acid. That's the beauty of equilibrium reactions and the principle of microscopic reversibility. If I know a mechanism in the forward direction, the reverse of that mechanism must be exactly the same. Atom for atom, bond for bond, arrow for arrow. And the hydrolysis of an ester is no exception. Here is our reaction card for the Fischer esterification. Our three-phrase sentence: a carboxylic acid reacts with an alcohol and acid to form an ester. We need to know that three-phrase sentence in all possible combinations. A carboxylic acid reacts with an alcohol and acid to form an ester. Alcohol and acid turns a carboxylic acid into an ester, and an ester is made when a carboxylic acid reacts with an alcohol under acidic condition. Some notes for this reaction: it is an equilibrium reaction. We can go forward or backward by hydrolyzing the ester with an acid and water. Some tags for this reaction: this is a non-regioselective reaction. It doesn't really fit into our concept of regioselectivity. In regioselectivity, we're reacting with one region of a molecule in preference to another region of a molecule. Here, there's only one reactive site, so it's non-regioselective. This is also non-stereoselective. We're not even forming a stereocenter in our product. And it is redox neutral. Both the starting carboxylic acid and the ester are at the 3-CZ bond oxidation level.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.